For problem 7.65, we have a common source amplifier, okay, with the process transconductance of 400 microamperes per square volts and an aspect ratio of 10, a drain current of 320 microamperes, and a drain resistance of 10k ohm. Okay, so common source means that the source is grounded. Okay. Now, for this particular circuit, the input impedance, so for part A, we need to define the input resistance. We have to define this gain here, AV0, and the output resistance. So for this particular circuit, we know that the input resistance is infinite. Okay, that's one of the qualities of this uh, particular topology, this common source amplifier. Okay, so that's the answer. It's infinite. Okay, because if we look at the circuit, we see that the impedance is actually infinite. So there's an analysis in the book, and then you can read that if you want, but that's the result. So the input resistance is infinite. Now for AV0, we have that AV0 is equals to the transconductance, so minus the transconductance times the drain resistance. Okay, and what's the transconductance? So for this topology, the transconductance is equals to 2 times ID. Okay, not for this topology, but the transconductance itself, it's 2 times ID divided by the overdrive voltage. And this means that GM is equals to 2 times ID. Okay, so ID is equals to, in our case, 320 microamperes. But what's V0? So V0 is equals to the square root of 2 times ID divided by the process transconductance times the aspect ratio. And we know these three parameters, so if we substitute the drain current and the process transconductance and the aspect ratio from the problem statement here, we get that the overdrive voltage is 0.4 volts. So this one here is divided by 0.4 volts. So the transconductance Gm is equals to 1.6 milliamperes per volt. Now that we have the transconductance, we can calculate AV0 because it's just like minus 1.6 milliamperes per volt times the drain resistance, which is 10k. Okay, so AV0 here, the output gain is minus 16 volt per volt. That's the second result. And for the output resistance, so RO here, we know that for this particular topology is just the drain resistance, which in our case is 10k ohm. Okay. Now for part B of these questions, if we consider that we have a load resistance connected at the output, right, at the drain of this topology, we need to find the overall voltage gain, so JV. So for this particular topology, we know that the overall gain is equals to AV0 times RL, which is it's like a voltage divider between RL and the output resistance. Okay, which in our case is just that minus 16 volt per volt times the load resistance 10k divided by the load resistance plus the output resistance, which was RD, which is also 10k. So this gives us minus 16 divided by 2, which is minus 8 volt per volt. And there's another part that if the peak voltage, if we want a 0.2 peak voltage at the output, What should be the amplitude of, what's the amplitude of the input signal, V signal? So if you remember, this overall gain here is actually the relationship between V out and V signal. So if we want a V out peak of 0.2, right? We can use this overall voltage gain to calculate V signal. So V signal peak should be equals to V out peak times the overall voltage gain, and this gives us a V signal peak that's equals to minus 8 volt per volt times 0.2. Oh, sorry, no, that's not correct. This is not correct. It should be, sorry, divided by the voltage gain. Okay, so yeah, so V signal peak should be equals to 0.2 volts divided by 8 volt per volt, which gives us 25 millivolts. And that's the answer for this part of the circuit.